Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Most stones removed with same row or column. Leetcode 947. In this problem, we are given n stones placed on a 2D plane at some integer coordinate points. Each coordinate point may have at most one stone. A stone can be removed if it shares the same row or same column as another stone that has not been removed. Then given an array stones of length n where stones I is equal to xi, yi representing the location of the ith stone, we should return the largest number of stones that can be removed. Then in example 1, we can see that we are given 6 stones at different positions. So let's visualize this a bit. We can see that because xi and yi are positive integers, I am just drawing the stone as a cells in the matrix. So for example, stone 0, 0 is this one, stone 0, 1 is this one, stone 1, 0 is this one, and so on. Now in the problem, it was mentioned that we can remove the stone if it shares the same row or same column with another stone. So let's start with stone at 0, 0, and then we check if there exists some stone with same row and column. And we find two stones at 0, 1 and 1, 0 that share the same row and column with stone at 0, 0. So we get rid of them. Then we see if for stone at 0, 1, there is any other stone in its row or column. And we can see stone at 2, 1 share the same column. So we get rid of it. And similarly, we clear the stone at 2, 2 as it shares the same row with stone at 2, 1. Then we also clear out the stone at 1, 2 as it shares the same row with stone at 1, 0 or same column with stone at 2, 2. So only stone remaining for us is 0, 0, and hence we return 5 as we were given 6 stones initially, but only one stone remained. So we could remove 5 stones, and that will be our answer. Now from this example, if we look this diagram carefully, we can see that if two stones share the same row or same column, that means they form an edge connecting them in the graph. For example, stone at 0, 0 shares the same row with stone at 0, 1 and same column with stone at 1, 0. Note that it is not a directed graph, but an undirected one. I have shown the arrows by mistake, so please ignore them. Then the second thing we can see is if the graph is connected or the subgraph is connected, only one stone remains. So for example, in our case, we kept 0, 0, but then we got rid of 0, 1, 1, 0, and because of that, we got rid of 2, 1 or 1, 2 and 2, 2, right? Now let's look at second example for more understanding. Here we are given 5 stones and the stones are placed in such a way that these 4 stones actually share row and column somehow. So out of these, only one stone can remain. So suppose we retain stone at 0, 0, but we get rid of other 3 stones, right? And the stone at center does not share any row or column with any other stone. So we retain it as well. And finally, because we were given 5 stone and we retained 2 stones, we will return 3 as an answer because we removed 3 stones. So again, in the graphical representation, we can see that these 4 stones were connected through row or column. So we retain only one stone. And here this was like a second disconnected component. So we retain one stone there as well. So in general, our answer will be if capital N is our total number of stones and small n is our number of components, then we will retain only one stone in each component. And because we have to return number of stones to be removed, so our answer will be n minus n, right? Now in terms of solution, there are multiple solutions possible. So if you look at this problem carefully, this problem is very similar to number of islands problem, where we start the DFS and sing the whole island when we are visiting it and then count number of islands. So here also we will be solving the problem using the DFS in a similar way. But another way which is more appropriate for this problem is using union find, where we can union the stones based on the row and column and then count the number of components in that union and then again return the answer as n minus n. And as I haven't covered union find algorithm yet, we will be solving it using DFS for now, but I will bring a follow-up after this to cover up the union find approach. Now for our DFS solution, we have two approaches possible. One way can be that we explicitly build the graph by iterating on the stones and then building the edge whenever we see a common row or column between the stones. Then we can run the DFS to see how many connected components we have. Another way can be that we don't have to build the graph, but we run the DFS on the stones and we can see if the stones are part of the same component or not by using the visited set when we are running a DFS. And we will be using the second approach in this demonstration, but I have covered both the approaches on my blog in the calling method, that is remove stones method. initially our visited set will be empty. And in the given stones array, the first stone is at coordinate 0, 0, and it is not visited yet. So we increase the number of components, let's say C equal to 1, because we are starting to explore a new connected components of stones. And now we start the DFS, so we visit the stone at 0, 0 and add it to the visited set. Now we continue with our DFS and see who are the neighbors of 0, 0. It is 0, 2 and 2, 0. So we visit them one by one. First, let's say we visit 0, 2. So we add it to the visited set. Then we go further deep down and check who is the neighbor of 0, 2. It is 2, 2 and 0, 0, right? But 0, 0 is already visited. So we will visit 2, 2 and add it to the visited set. Then we see who is the unvisited neighbor of 2, 2. It is 2, 0. So we will also add it to the visited set. And now we come to 0, 0 again, and we had to visit 0, 2 earlier. But now it is already visited. So we will continue. And now we have visited all the stones through this DFS. So we will return to the calling method where we started the DFS. Now we continue our search for unvisited or unexplored stones. So we come to 2, 0. It is already in the visited set. Then we come to stone at 1, 1. So we say that this is not visited. So this signifies it's a new connected component. So that means we should increase the number of connected components to 2. So we will again start the DFS from here and start exploring. So now we start the DFS from 1, 1 and add it to the visited set. And we can see that there is no other stone which shares a row or column with stone at 1, 1. So we will return. And now we come to stone at 2, 0. We can see that it is already visited. And finally we come to the last stone, that is stone at 2, 2. We can see that that is also visited. So in the end, our number of connected components is equal to 2. And our answer, that is number of stones to be removed, will be 5 minus 2, because we retain just 2 stones. And that's why 3 will be our answer. Now let's jump into the code part. So first thing we will do is define the visited set of stone coordinates, tracking the stones we have visited so far. And let's define number of components. So that will be initially equal to 0. Now we will start going through each stone in the stones array. Let u be that stone. And we check if it's already visited. So if it's not, then we will start the DFS. We will pass the stone coordinate visited set so that DFS can update it, and pass the stones array. We will increment the number of components by 1. And finally, we return number of removed stones as stones length minus number of components. Now let's write our DFS. So it will take the stone coordinate that we are visiting, the visited set, and the stones array. Now we will add the stones coordinate to the visited set and find its neighbor, that is stone with same row or column. So we will again start iterating on the stones array, say with iterator v, and check if this stone is not already visited, and if u and v have same row or u and v have same column, that means both u and v are connected and are part of the same component. So we will continue with our DFS and visit v as well, and that's it. Now let's run this code. Let's submit this code. Awesome. In terms of time complexity, it is O of n square, where n is the number of stones. And the reason is we are actually running this loop here, which takes O of n time. And inside this loop, we are running DFS. And within DFS, we are again looping on the stones array. So that again takes O of n. So because of this nested nature of the loops, we get a time complexity as O of n square. And in terms of space complexity, it is O of n again, because we are using the recursion stack, and in the worst case, the recursion depth can be O of n. Also, we use visited set, which again takes O of n space. So overall, the space complexity is O of n. So that's it for today. I hope this video was useful to you. If it was, please like, share, and subscribe. And leave any comments or questions in the comments below. Have a nice time. Thank you.